Hey, hello guys. I was able to simulate the amplifier that on the last video that I uploaded the other day about this high power lateral MOSFET audio amplifier capable of delivering about 550 watts RMS into a 4 ohms load at 0.05% total harmonic distortion. So I was able to simulate it at the beginning when I placing the components into the simulator. I have some problems. I guess the trim pod, I have to change the value to a larger value, 2K, a 2K resistor instead of 500 as the original. I gotta zoom here. This you can see the pot 2, the original value is 500 ohms, but I noticed that the distortion was kind of high, so I had to use a larger value. Maybe it was giving too much current, and I'm not sure. I cannot tell you that's the reason. But what I did, I made the simulation. I read that on MOSFET you gotta set it to 20 kilohertz, so you can adjust the bias. So you need to lower the total the distortion. So what I do, I just give it a sine wave of 20 kilohertz. Let's say 100 millivolts. I'm not sure if I'm doing it correctly, but anyway, that's. Let's see. I'm going to activate the simulation, and this is the old scope. I'm gonna make it a little larger for you guys so you guys can see. Let me see how's this going to respond. All right, let me activate the simulation. Let me see. As you can see, the sine wave looks pretty clean. As you can see, it's nice and clean. You don't see anomaly here in the middle, the middle line of the oscilloscope. It looks pretty nice and clean. What I'm gonna do, I'm going to adjust the bias to show you how it was before the anomaly, the distortion. So I'm going to show you that in a minute. So it was sort of like this. Let me adjust this. Oh, I forgot 59.55%. So now I'm going to adjust it so you guys can see the anomaly. There you go. That's the anomaly I was talking about. Since I moved the bias, it was doing this. As you can see, let me see. I wish I can zoom here this. Let me see if I can make it larger. This oscilloscopio. Let me see if I can make it larger. As you can see here, there is anomaly right here in the middle. You can see there is a little step, some kind of step. So to avoid that step, I had to adjust the bias. So I need to write it down, the final bias adjustments. So I got 20 kilohertz. So I'm going to adjust it to eliminate and clean out that anomaly, that steps. You can see that step over there, like a ladder step, something like that probably. Okay, I'm going to adjust the bias. So to eliminate the distortion. That's a better way to say it, distortion. Okay, 59% is coming out. It's cleaning out. Okay, let me see a little bit more to eliminate that distortion. I think 59.35%, and I see that it's pretty clean. The one thing that I didn't like is the square wave. It looks bad. It looks pretty bad. So I'm not sure if this is correct. You're not supposed to be like this. Well, I got 20 kilohertz right now. Maybe I gotta find out why it's doing that. You're not supposed to doing that. You can see there's a little like a little mountain on top. So I don't like that. So I gotta figure out how to eliminate that. It's kind of weird. I gotta figure out. Okay, so now let's change this to 1 kilohertz sine wave, and let's see how it's gonna respond right now. Now that I changed the bias. There you go. Now it's coming out nice and clean. The total harmonic distortion. Well, I gotta increase the power to see. Going to increase the power to 900. 900 millivolts. All right, let me see. It's coming out nice and clean. All right, we have 356 watts to a 4 ohms low. That's not bad at all. 4 ohms low, as you can see here. But I gotta figure out why it's doing that, because this is the original schematic. Maybe it's because I'm not using the actual power MOSFET that requires this circuit. As you can see, this circuit, it used 2SK1058 MOSFET, lateral MOSFET, and the other one is, let me zoom here so you guys can see better clearly. As you can see here, the other semiconductor MOSFETs, 2SJ162. So I did not have those, so I had to use these MOSFETs, and probably that's the reason. IRFP 240, and I'm using the other one, IRFP 9240. So probably because I'm not using the correct semiconductors, probably that's the reason why. But it's working. Actually, it's working. Also, the transistor that I do not have on the simulation is this one here. I do not have 2SB649. I do not have that one, and the 2SD669. I did not have that available on the simulation, so I just used a common MJE350G. G. Oh my god. And the other one is the Q7. It's MJE340G. So that's the one that I use instead, because I didn't have those available. Well, actually, it's pretty powerful. Let me see. I'm going to increase the amplitude to see where's the clipping is going to be. To see. Okay, let's see. We got 900 right now millivolts sine wave. I'm going to increase the amplitude. Okay, we got almost 1 volt peak sine wave, and we have 439 watts. According to the circuit, is supposed to be giving you 550 watts. So it's not giving actually 550 watts. So maybe I gotta increase the amplitude a little bit more. Let me see. Okay, 1.1 volt peak. We have 528 watts. 1.2, we have 631 watts. Total harmonic distortion is 0.195, and we have 50 volt AC coming out from this load. So I have a meter here to measure the voltage in AC, and we have actually 50 volts AC. It's not bad at all. I mean, I found this circuit really interesting. I purchased the book a long time ago when I was interested in electronics. That was a long time ago. So I found it somewhere and on PDF, and I found this circuit really interesting. Here I do not have the correct transistor. I supposed to have this transistor in particular, 2N5551, and the other one is 2N5401. Those are really common to find. I changed this R23 to let me see, what was 900 something. I think I changed it to just to get a little bit more power. 950 ohms. The original value is 1.2K, and then I changed the feedback resistor, the 47K, to I think it's 68 or no 56. Negative feedback resistor, 56K. Also, what else I did? I think I changed this center diode. I think it's the same value. This one is 1N4738 is 3.9 volt center diode. Let me see. I gotta make sure it's correct. Center. Let me see. It's 3.9 centers. All right. Let me see. It's this one here. 3.9. There you go. Right here. 3.9 volts and 1N4730A. So that's the one that I use here. So it's the same. It's the same value. No problem. It's the same. As you can see here, it's 3.9 volt. I also add the protection circuit for the. I don't think it's. I'm not sure if I'm doing it correctly. Let me know, guys, if you are expert on this. Let me know. But I add this protection circuit, the center diode. I always seen these diodes on MOSFET audio amplifiers. So I'm not sure if I'm doing this correctly. So basically, this is the bias adjustment over here. The only thing that I'm a little worried about it is the standby current. I don't want the amplifier to be in idle, high idle. So let me see how much current is draining on standby mode. So I need to check. I need to check that just to make sure it's not draining too much current. Because there is a balance. You gotta have a good bias reading to lower the total harmonic distortion, but also at the same time you gotta make sure it's not conducting too much current, because it's gonna keep the power MOSFET really hot. So it's a balance that you gotta check. You gotta make sure everything is balanced. So it's difficult. It is difficult to keep that. Okay, let me see. This meter here is measuring the current, DC current, in series with the fuse. Let me see how much current is draining. This one here, this little window, this millivolts. This little window is to measure the voltage across this. I can say source resistor. All right, let's see. To activate the simulation to see what we get. Okay, I have a 48 millivolts. So wow, let me see how much current is draining right now from the right here. Okay, I think it's a little hot. I mean, a little too high. Let me change this appearance to make it larger so you guys can see. This is really important so you guys can see better. All right, let's see. It's okay. Okay, we have 102 milliamps DC. The amplifier is draining right now 620, about 630 milliamps from this rail. You can see from this rail. I'm measuring this rail right here. I'll change the color to. Let's see. I don't think I'll be able to do that right now because it's in simulation. Let me see. Segment color. Let's change it to red. So you know the red. Yeah. Let's change it to red. There you go. So that's the current that is passing through. We had 102 milliamps. Basically, I'm thinking that might be on the area of Class A, probably. It's supposed to be Class AB. Class A, maybe? No. It cannot be Class A. It's not Class A. No, it's not. Okay, let me go back a little bit. Let me adjust the bias, just not to get too much. Okay, we have. No, it's not Class A because Class A is conducting all the time, the majority of the time. So no, it's not Class A. Okay, let me see. Going to adjust this. Okay, 101 milliamps, 99. Okay, we got 46 millivolts. So it's 59.3%. Okay, we had 101 milliamps. Okay, that is okay. 100. You don't need to be that exaggerate. Okay, 100. All right, let's see. All right, let me see. Let me activate the low. Check one more time. Gotta make sure it's correct. All right, let's see. Okay, we have right now a 4 ohms low. I'm wondering how much power you can get with 2 ohms or 2 ohms low. Not recommended. I'm just curious. I'm not really recommended this. 2 ohms low. Let me see how much power you can get. All right, let's see. Okay, 2 ohms low. MOSFET amplifier. Let's see. All right, we have. Damn. Okay, it blow the fuses because more current is needed. So yeah, so it's not recommended because it blows the fuse. As you can see, the 50 amp fuse it was blow. So just for curiosity, I'm going to change this fuse to a 30 amps fuse. Just for curiosity, not recommended. I will not recommend to do this. To have a 2 ohms low on the amplifier. No, I really don't recommend that. Okay, let's change it to 30 amps. Just to see, just for fun, not to do it in reality. All right, let's see. We have, okay. Let me see. We have 869, 870 watts. The total harmonic distortion is 0.05A. And it's draining 9 amps of current. So right now I'm going to increase the amplitude to see how it's going to behave this circuit. This is really interesting, guys. All right, let's see. 900. Okay, we got 1 volt peak, and we have. Let me see. We have 880 watts. All right, how much current we are draining right now from the supply voltage? We got 9 amps. Okay, we got 9.4 amps, 879 watts. We have no, it's weird. It says 41 volts. Oh yeah, I know why it's doing that. Yeah. Okay, and we are going to increase the amplitude a little bit more. Okay, I think it's clipping right now. No, it's not clipping. Okay, we got 1,000 watts, 10 amps of draining. It's draining about 10 amps, 0.096% total harmonic distortion, 1,000 watts. That's pretty good. I'm going to increase. This is just for fun, guys. Don't do this. Do not try this at home. This is too dangerous. All right, let's see. 1.2 volt peak. We got 1,265 watts, 11 amps of current. We got distortion is kind of high right now. We have 0.219% total harmonic distortion. 1.3 clipping. There you go. We got a clipping. 1,450 kW. Whoa. At 8,447 watts. Oh, Jesus Christ. I'm just testing this, guys. So I mean, this is just for fun. I mean, and it's kind of expensive too. So I was reading the book, and I realized that when you do this type of project, you will spend a lot of money on parts and also prototype. So, but it's good to have these videos. That's why I'm making this video. So if you guys want to try out something different, high power amplifier, so at least you got maybe some idea of how this thing is behave. I will say that this might cost. Let's see, if I'm going to build this, you gotta create the PCBs. You gotta create 2 PCBs, 1 driver PCB. Like one sample, you have to make this PCB, all this circuit, this part of the circuit, and the OPS powered circuit. Now that I learned that the output of the audio amplifier, where the the larger components, as the power semiconductors, MOSFET or BGT, those are called OPS. That's OPS. So that's what I learned from the book, from this book. J. Randy Sloan, this is the writer of that book, and this is his schematic. So I will say that if you are to build this amplifier, I might say you need at least the transformer to get 550 watts per channel. I will say 1,000 kVA transformer. You need to have one of those, and you need to have at least. I think I was reading a Douglas South book, and I think for each 100 watts you need about 10,000 microfarad. I think you need 10,000 microfarad. So you will need a I think 5 or 6 10,000 microfarad capacitor. So you will need 12 capacitors for the power supply, and a larger heat sinks to to eliminate the heat. So yeah, this is a really interesting circuit. I like this one here. Alright, so I will call this one successfully simulated. I think it's correct. One sample, let me test. I always do that. I'm going to test the lowest distortion possible. I'm going to I'm going to change the amplitude input sine wave to a 10 millivolt sine wave, just to see. Alright, let me see how much lower distortion I can get from the total harmonic distortion window. I need to see that. Alright, let's see. Alright, there you go, the sine wave. We have, oh, that's pretty good. That's pretty good. Alright, the amplitude sine wave right now is 10 millivolts, 1 kilohertz sine wave. We had 0.001%. That's pretty good. And we had 44.023 milliwatts. So basically it's like you listen to the music really low. So that's pretty, look at that, the sine wave looks pretty clean. It looks nice and clean, as you can see here on this illustration. I mean the sine wave, it looks pretty clean. I don't see any anomaly. The only thing that bothers me is the square wave. Maybe I gotta find out how to get rid of this. Anyway, I don't think it's a big deal. I don't think but I will figure out. I will figure out how to smooth out the this part of the square wave, or maybe it's not possible because of the circuit. Maybe. Well, okay, that's it, guys. Just wanted to show you that I already complete the simulation successfully. I think works pretty good. Might be interesting to create this this PCB, the IPS PCB and the power PCB. But well, that's it, guys. I hope you like this video. Please subscribe to my channel and share this video. I'm not an expert, but at least I got a little knowledge, not that much. But share this video for your friends that like this electronics. Probably they can use this example to figure out stuff. Alright, guys, have a good day, and I hope you like this video. Alright, guys.